All right, let's see. I was going to talk about the homework number 2 briefly. I was going to do that at the Q&A last night, but we didn't have anybody at the Q&A, so we didn't actually have one. Let me say something about what you're doing in homework 2, number 2. We are looking at success-fail outcomes for each of a bunch of people that are enrolled in a clinical trial. We can, because of that, if we treat all of the individuals as a Bernoulli trial, yes or no, do you have an adverse event that has to be reported to the study team? Then what we can say is for the first, let me put a title up here. For the clinical trial problem, we started by saying there's a probability P, probability of an adverse event for any one study participant. And we put a prior distribution on this parameter. We said prior was that P follows the beta distribution with parameters 1 and 999. That particular distribution has expected value equal to 1 in 1,000. Our prior belief in this example was that adverse events happen at a rate of 1 in 1,000. Then we observed some data. So one way to write this is after observing 100 individuals, I think that's what we said. Let me open up the homework. We initially saw 100 individuals and 2 of them had adverse events. So we could say that X, let's define X as number of adverse events in first 100 subjects. Then we can say that X is binomial. Number of, quote, successes out of N trials, 100, quote, trials. Each time, probability of an adverse event is P, whatever P is. Okay, so then if we saw, like we said in the homework, if we saw X equals 2, then the likelihood L of P when X is equal to 2 would be the binomial PMF evaluated at X equal 2. We've seen likelihoods defined as products of PMFs or PDFs. So we could represent our 100 zeros and ones as a random sample of size 100 from a Bernoulli, in which case the likelihood would be a product over I equal 1 to 100, the Bernoulli PMF. It's equivalent to say we observed 100 and there were 2 adverse events out of those 100. That's a binomial approach. So whether we treat it like binomial or Bernoulli, we'll get the same results. Here I'm treating our data, x, capital X, as binomial. So the likelihood is just the binomial PMF. In this case, it would be 100 choose 2 times p to the 2, 1 minus p to the 100 minus 2. So we have a likelihood and we have a prior. Then the posterior, after observing these 100 individuals with 2 adverse events, the posterior we'll say is G of P given the data. This is Bayes' rule, likelihood of P times prior, let's do F. F of P. And because we're treating P as a continuous random variable, what goes in the denominator of Bayes' rule is an integral. The integral over all P, L of P, F of P, dP. So integrate from 0 to 1 of that quantity. That will give us back a function of P. And it is a probability distribution. It integrates to 1. It's the posterior of P. Let's see how this looks in R. Let me go get text editor. And write some stuff down. Okay, so clinical trial from homework 2. Our prior distribution I'm going to write a function to represent it. This will make it easy to plot it and also to integrate it. I'm going to say prior f is a function of p. And all it's going to return is the beta PDF. PDFs or PMFs come from D and then the distribution name. D beta, D binom, D norm. So evaluate the beta distribution at P when alpha is 1 and beta is 999. Okay, so if we do this, let's plot the prior. So I'll do plot. Let's set up an empty plot, and then I'm going to use the curve function to plot it. I can say curve prior f, and then the arguments are from 2. So draw this curve from 0 to 1, because the p can be any number between 0 and 1. In order to get a plot ready, let me see, actually this might work just fine without doing a plot. Let me check. Whoops, okay, that's all right. So prior f has been defined, and let me see if this works. It does, okay. That is the prior, and it looks, it's kind of hard to see what it's doing, but because of our setting the prior mean equal to 1 over 1,000, all the probability mass is piled over there close to 0. This actually looks like that distribution looks like this, from 0 to 1. prior for P. It spikes and then tails off very quickly. Now let's incorporate data. After observing 100 participants for whom there were 2 adverse events, then the likelihood, I'm going to make it a function 2, let me call it likelihood 1. This is the initial likelihood after we observe just 100. But then we're going to have another one after we observe another 100. My likelihood function is, like we said back here, a binomial PMF. So give me the probability function, d binom. Evaluate it at 2 successes out of 100 trials with probability p of success each time. We don't know p, so we're going to evaluate this function as a function of p. Let me say likelihood after observing. Now let's do posterior. Posterior after observing above. And I'll say posterior f is a function of p. And the way we define it is a likelihood times a prior divided by normalizing constant. I'll say norm constant. Where normalizing constant is the integral of likelihood times prior. I can define that here. Let's say norm constant is integrate like, okay, I'm going to make another function that is the product of those 2 prior and likelihood functions. Prior times likelihood, function of p, and all it's going to do is multiply prior times likelihood. Now integrate that. Integrate the function prior x like f. The integrate function has lower and upper arguments. So from 0 to 1, integrate that. And then that's what goes in the denominator of the posterior calculation. So let's run this and see what we've got. Oops. Okay, so now post underscore f, if I evaluate it at p, will be the posterior distribution. And we could draw this, could add it to the curve up above, curve post f from 0 to 1, add equals true. And I'll go ahead and give it a different color. Add equal true means don't make a new plot. Like 1f times prior f. Non-numeric argument. Let's see. Whenever you use the integrate function, norm constant is the result of doing integrate. It actually is not a numerical value. There's a numerical value in there. Let's ask, what are the names of norm constant? There's something called value. So let's get that. And try again. Non-numeric argument. Okay, what's the problem? Like 1f.5 prior f.5. So why is that? Oh, I need to evaluate these at p. I was trying to do products of two functions. That's not defined. Okay, try again. And in the homework, so it did add a curve. There's a blue curve now. In the homework, I asked you to focus the picture over close to 0, because otherwise we can't see anything. So let's redo these pictures from 0 to 0.05. Just zooming in so that we can see a little better. 0 to 0.05. And let's redo this. Okay, so that one's a little easier to see. Prior had almost all the probability piled up really, really close to 0. Posterior, because we saw 2 out of 100 when we were expecting, according to our prior, just 1 out of 1,000, it increased, it pushed to bigger range the distribution of p. Combining our prior with the observed data, our beliefs were updated. And in particular, they were updated to have an increased expected number of adverse events. You can compute the expected number, by the way, using integrate. The expected value of a random variable, the expected value of p under the posterior is defined the way an expectation usually is defined. It is an integral of possibility times probability, roughly speaking. 0 to 1, integrate over all p of p times its probability distribution. So remember, this is like a weighted average. That's what an expectation is, expected value. Let's compute the posterior mean. I can do that by mean for, or let's say function, expected val function. And I'm going to define this as p times posterior of p. Then the expected value, posterior mean, would be integrate this. Integrate p times posterior of p from 0 to 1. Prior mean was 1 in 1,000. Expected val f not found. Posterior mean is almost 3 out of 1,000. And then you were given a second part where you updated with one more time. And there's two ways to do this. You can treat the posterior now as if it were the prior, and then compute a likelihood that reflects just the new 100 individuals. So if I treated the posterior as the prior now, I would say, let's now incorporate 100 observations with 3 successes. An alternative would be to go back to the original prior and now treat it like we have 200 observations with 5 adverse events. They will be equivalent. You'll get the same posteriors, same inferences. I won't give you all the code here, but it's the same approach. Define the likelihood after 100 more participants, this time with 3 adverse events. You could set your prior to be the posterior that we just computed. And then your likelihood would just be a binomial likelihood with 3 successes out of 100 trials. Everything else would be comparable. When you do it and add the curve, you'll see another curve that's shifted even further to the right. After seeing 100 individuals, our beliefs were updated by increasing what we expect P is. After seeing another 100 with, again, more than 1 in 1,000 rate of adverse events, it's going to push it even further to the right. Okay, are there any questions about how to do this? There was somebody on the discussion board who was confused on how to work with a continuous PDF. You need to be integrating, not summing, if you have a continuous distribution. All right. Then let's continue with linear regression. All right. Remember the big idea of regression. In its simplest form, we have a continuous response variable and a continuous predictor variable. Like we started with the response being weight and the predictor being height. And linear regression is saying there's a linear relationship on average between y and x. Not a deterministic one, like you tell me x, I know y exactly, but a relationship on average. The model is of the form, the response for individual I is equal to a line as a function of xi, that's the predictor variable for individual I, but then we're allowing for there to be random variability about these means. So we have what we called epsilons, and the epsilons are, for now, treated as a random sample, independent and identically distributed. The independent part is important, so is the identically distributed. But the classical assumption is that they are IID, also normal, mean 0 by construction, because they represent deviations from the best fitting line, and a constant variance sigma squared. So we said if you pick any value x, any predictor value x, call it x0, then the mean of y, according to the model, is the value of the line when x equals x0, that red dot. What we actually observe, if we were to sample repeatedly individuals with this predictor, would be a distribution sitting on top of the line, centered at the point of the line. This curve is bell-shaped because of the normality of the epsilons. It has a variance equal to sigma squared, and because sigma squared does not depend on x, if we were to move x0 up and down this line, slide it up and down, we would see this exact same curve sliding up and down the line because of the constant variance. If this picture, if the scatter plot was fanning out in larger values of x, then that would not apply. The variance is changing. It's not the same. It's not constant. In terms of interpreting regression coefficients, we said last time that beta 0 is an intercept, but we speak in terms of expected values or means in regression. So beta 0, yes, is an intercept, but specifically, it's an intercept for the mean relationship. It is the mean of y, mean response, when x equals 0. Similarly, we saw that beta 0 plus beta 1 is the mean. Let's not do that. Let's just say beta 1 right now is a mean difference. Beta 1 is a slope, so rise over run. But again, we speak in terms of means or expected values. So it's a difference in means of the response associated with a 1 unit increase in the x variable. Okay. We ended here, and what the next few slides are doing is making an argument that everything is regression. Okay, so most of what we do in statistics can be formulated in one way or another as a regression model. Here's the simplest possible regression model: one numeric variable, one numeric predictor. Here's another regression model that doesn't maybe seem like it is a regression model. This really is a two-sample comparison of means problem, where we have a continuous numerical response, in this case income, annual income, and x, our predictor variable, is not numeric, but it's categorical. We defined it arbitrarily to be equal to 0 if your degree type was arts, and 1 if your degree type was sciences. We can still write a regression model. It is, in fact, equivalent to doing a two-sample t-test to write this in this form. The response for individual I is an intercept plus a, quote, slope times x plus random error. What this means is the mean of y when x equals 0 is beta 0. And the mean of y when x equals 1 is beta 0 plus beta 1. I'll write this down real quick. Linear regression with binary predictor variable. Our model is yi equals intercept plus slope xi plus epsilon I, where the epsilons are IID, normal, 0, sigma squared. Then, because the epsilons have mean 0, this is equivalent to saying the mean of y equals beta 0 plus beta 1 xi. No epsilons anymore, because once you take the expected value, you're on the line. X can only be two things: 0 or 1. If arts, 1. If sciences. When x is 0, we have this mean relationship. Expected value of y is equal to beta 0 plus beta 1 times 0, or just beta 0. Beta 0 then, if you want to interpret it, what does it mean? In order to interpret a coefficient, what you need is an expression like this. Beta 0 equals something in terms of means. Similarly, if you want to interpret beta 1, you want beta 1 equals something in terms of means. That's what I'm wanting when I ask for interpretation. When x is 1, we have that the mean of y is beta 0 plus beta 1. And that means that beta 1 itself is the difference between those two. Beta 1 is mean difference in response comparing sciences to arts. Beta 1 is a mean difference. We have like a two-sample problem here, and a natural question would be, is the mean for the arts group the same as the mean for the sciences group? We could do that with a two-sample t-test. It turns out to be equivalent. That is equivalent to testing the null hypothesis that beta 1 equals 0. Because beta 1 is that mean difference that we wanted to do inference on. We can also think of beta 1 as like the degree effect. What's the effect on the mean of going from arts to sciences? So another kind of regression, not really thinking about lines and stuff, but it still works to do inference. Two-sample t-test is regression. And then let's start getting more sophisticated models. That simple linear regression model had one response, one predictor variable. But in the real world, any complex relationship will surely need additional variables, more than just one variable, to fully explain the relationships. For example, if we really wanted to look at weight in terms of height, we would want to know gender. We'd probably want to know race. We might want to know some genetic information. What kind of alleles do you have for specific genes? Overall healthfulness, smoking status, all kinds of things could conceivably be sources of variation in the population. So if you want to do inference on a response and in relation to a particular predictor, like in this case height, we want to do inference on the relationship between weight and height. We will have better inference if we include in the model the additional variables that will that also play a substantive role. If you don't have the important variables in the model, you might get an incomplete or even incorrect picture of the relationship between y and x. So you're familiar with the idea of confounding, and Simpson's paradox, for example. That is an illustration of you can fit a model, but if there is a so-called lurking variable that you did not incorporate into the model, it can completely bias the results. For example, I could cook up some numbers that have salary in terms of type of degree earned, like we were looking at a minute ago, arts versus sciences, and make it, okay, so arts versus sciences, and we could have males versus females. So suppose we just make up some numbers, salaries for people who got arts or science, and we also know their gender. You can cook up examples where, for example, the mean difference in salary between women and men looks like there's discrimination toward women. The average for the men is higher than that for the women. But that can be completely artificial. You can cook up the numbers so that the reality is the exact opposite, that a woman tends to make more than a man if you look within the different majors. So I'll do that later if we have time, but you can make up examples where if you don't incorporate, in that case, degree type, if you only looked at men versus women, you would get one answer. But if you incorporated an important lurking variable, your answer's changed, and it could even be swapped. Looking at it one way suggests that there's discrimination against women. Looking at it adjusted for gender, I can make up the numbers so that it actually looks like there's discrimination the other way. So this slide is about y and x, and now we want to start incorporating additional predictor variables or covariates. Here I have weight and height, just like before, but now we're going to include a term for gender. The model looks like this. Linear regression means you're going to have a linear combination of some predictor variables. Beta 0 is an intercept still, beta 1 xi, that's the slope in terms of x, and beta 2 zi. Zi is binary here. So the actual picture that we are reflecting is up here. The model that we just fit says beta 0 would be the mean response of y when x is 0 and z is 0. So this line right here is for the females. Z equals 0, and beta 0 is this value down here, the y-intercept when x equals 0 among the females. If we go to males, then this z becomes 1, and the beta 2 is now in the model. So the intercept for the line, whenever x is 0, but men are being looked at, would be beta 0 plus beta 2. The intercept for the line for men is beta 0 plus beta 2. And the way we have this model written, we have a slope beta 1 that applies to the females and to the males. This model is allowing for a linear relationship between height and weight and a constant shift between men and women. But it's restricting the slope to be the same for men and women. That may or may not be appropriate. What we can do to make it even more flexible is allow for both gender-specific intercepts and gender-specific slopes. That's what this model is doing. This is a model with what's called an interaction in it. yi, the response, intercept, plus a slope in x, plus a slope in z, plus this additional coefficient that is the product of x and z. What this does, let me write this down over here. If we have yi equals beta 0 plus beta 1 xi plus beta 2 zi plus beta 3 product of those two, xi times zi plus epsilon I. Then we can think about the different scenarios. For women who have z equal to 0, the mean relationship is expected y beta 0 plus beta 1 xi plus beta 2. No, not beta 2, because z is equal to 0. So the mean relationship for women is the model when you plug in z equals 0. All that's left is beta 0 plus beta 1 xi. In this picture, we would have a line that has its own intercept and potentially its own slope for the females down here. Beta 0 plus beta 1x. Whereas for men, with z equal 1, we have mean equal to beta 0 plus beta 1 xi plus beta 2, and then plus beta 3 xi again. All we did was plug in 1 for z. And then if I join like terms, we can write this as beta 0 plus beta 2 plus beta 1 plus beta 3 xi, which is another line. But this line is allowed to be different from the one for the women in terms of both intercept and slope. So we will use interactions here and there. Let me show you this slide briefly. The point of this slide is to say Anova, which we might think of as being its own thing. It's presented as its own thing. It's this analysis of variance. It looks different from t-tests. The models look different. We might say the response for individual I in comparison group J and individual I comparison group J with gender K. Actually, I think it goes with degree I, gender J, and this is the kth replicate in that group. But the mean is written a little differently. We write it as an overall mean plus a degree effect and plus a gender effect. And those degree effects are restricted to sum to 0. The gender effects are restricted to sum to 0. That's for identifiability purposes. Otherwise, you have too many parameters to estimate. But this here is another way of saying Anova. This is an Anova model. The Anova null hypothesis is that all the terms other than that intercept or overall mean are equal to 0. There is no difference between the means that we're considering. And that also can be written equivalently as a regression model. So Anova is regression. In particular, I can write it like this: beta 0 plus beta 1 xi plus beta 2 zi. And now my null hypothesis that's equivalent to the Anova null hypothesis is that both of those beta coefficients, beta 1 and beta 2, equal 0. Beta 1 is a degree effect. Beta 2 is a gender effect. Is there any effect, is the Anova question. So if there is no effect, then both of those would be equal to 0. Whether we're doing usual simple linear regression, t-tests, Anova, and we can get as sophisticated and complicated as we want in terms of having tons of variables in the model, interactions. Most everything in statistics can be oriented as a regression model. Still have a few minutes. Let me start with this material, which is taking the expression for regression models and making them more compact and therefore easier for us to work with in what follows. So here's the simple linear regression model. yi is beta 0 plus beta 1 xi plus epsilon I. And let's say that n is the sample size. If the model is yi, beta 0 plus beta 1 xi plus epsilons, then we could represent all of our data like this. We could say individual 1 is beta 0 plus beta 1 x1 plus epsilon 1. And similarly, individual 2, beta 0, beta 1, x2, epsilon 2. Dot, 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 yn is its expression, xn, epsilon n. Another way to write that this is equivalent to a vector y. So a vector is like a column of numbers. Y, we could say, is n by 1. N rows, 1 column. And y can be written as a matrix X that, in this case, is n by 2 times a vector of coefficients. In this case, 2 by 1, because we have beta 0 and beta 1, plus a vector of residual terms. Y is the vector y1, y2, yn. X is the matrix that has 1s in the first column and then the x's in the second column. Beta is a 2 vector. So let me focus in on this just for a moment, this piece right here. X beta, we're going to see that a lot this semester because we're going to represent most of what we do as regression models. And it turns out that any regression model can be written, well, any linear regression model can be written in this matrix form in the blue on the right. Y equals X beta plus epsilon. Let me go to a new slide and talk about this X beta thing. X is n by p, generally, however many coefficients we have in the model, and beta is p by 1. So if X looks like 1, 1, dot, 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 1, and let's do the simplest case with just a single X, x1, x2, xn, then beta is this vector containing beta 0 and beta 1. N by 2, 2 by 1 is going to give us, it's going to give us an n by 1 column vector. N by 2 times a 2 by 1 gives us n by 1. And the first element is going to be take the dot product of the first row with the betas. What that means is you would do 1 times beta 0 plus x0 times x1 plus x1 times beta 1. The second row would be dot product of this with the betas. So we would have beta 0 plus beta 1 x2, and so on. That x beta is a compact way to represent this regression model for all of our data. We're going to use it. You probably don't see why we care that we can write it this way just yet, but it becomes clear like Friday. We will use this expression to figure out solutions to the regression problem. In particular, we're going to have an expression like this that says, if you tell me what X is, that defines the model you want. X is called a model or design matrix because it reflects the treatment groups and different covariates and everything. It's all in capital X. So if you have that capital X and you use it to write a regression model, y equal x beta plus epsilon, then the estimates, maximum likelihood estimates of that vector of coefficients can be gotten with this expression. And this holds regardless of what capital X is. Any linear regression model, you can estimate its coefficients using this matrix operation. And using those design matrix pieces, we can get the variances and therefore standard deviations or standard errors of the coefficients. And if we have an estimate and a standard deviation, we're almost ready to do inference. The only other piece of the puzzle we need is a distribution for the betas, and we'll see that later. We're going to use what's called a likelihood ratio test in the context of regression. Okay, questions? That was a lot of material, but all right, I will see you Friday.